Good afternoon, all of you. Welcome to the technical talk, which is being presented by Dr. Mukesh Kumar Singh. Dr. Mukesh Kumar Singh is a BTech and MTech from Chhatrapati Shahuji Maharaj University, and then he has done his PhD at IIT Delhi under the guidance of Dr. Behra. And as far as his experience goes, he has a small stint in textile industry in Pashupati, and thereafter over 21 years he is academician only. He has worked in Government Central Textile Institute, which is now UP Textile Technology Institute. He has worked as lecturer, then professors, and then he was director, because UPTTI director is on not long-term basis. It is for 3-4 years, something like that. So he is immediate past director of UPTTI, and now he is professor and dean academics in the same institute, that UPTTI. He has authored 4 books, and as his professional experience, he has over 50 papers to his credit, 25 invited talks, 32 professional trainings, and he is very able professor. He has organized, he is always active. He has organized around 4 international conferences and 2 national conferences, and so many seminars and webinars. He is presently the chairman of Board of Studies of Abdul Kalam Technical University. He is member of RDC, which select the PhD aspirants of AKTU. Then he is a member of ERP also of AKTU. AKTU means Abdul Kalam Technical University. And I would expect a great applause from the participants that Dr. Mukesh Kumar Singh, for his technical work and technical development, has been awarded by UP government, UP Ratna Award. So this is a great thing he has achieved, which is to be commended upon. And today, Dr. Mukesh Kumar Singh will be speaking on the smart textiles for emerging business opportunities, which is an emerging area. I will give a small brief of small textiles, and then leave over to Dr. Mukesh Kumar Singh to tell you in detail about the smart textiles. Smart textiles are categorized into passive, active, and very active. The world market of smart textiles was about 3 billion in 2021, and is expected to be 13.60 billion by 2027. North with the CAGR of 29.1% from 2022 to 2027. The major producer of smart textiles is North America. It is on top. And in Asia Pacific region, China and India are a major player. And smart textiles means growth is that can be credited to this wearable electronics. Nowadays, the trend for wearable electronics is increasing every day, and that wearable electronics will lead the growth of smart textiles. And then second one comes the defense and military establishment, and that is the largest market currently. And there the use of this smart textiles will increase on the basis of defense budget of the concerned countries. Then next comes the sports and fitness, which is of consumers use. Sports and fitness is another growing area of smart textiles. So I mean to say that there are very good opportunities for smart textiles grow in India. India has got very small share of business, global business and smart textiles, and we can do a lot. So that all we will hear from Dr. Mukesh, who is the expert in smart textiles. He has done a lot of work in being in GCTI, in lab also. His lab is also doing a lot of work in smart textiles for defense personnel. They have developed many gadgets and textile products which are being used by the army nowadays. So with this short introduction of Dr. Mukesh Kumar Singh, I will give the floor to Dr. Mukesh Kumar Singh to tell you about the different varieties of smart textiles and what are the emerging business opportunities in this area. Dr. Mukesh Kumar Singh.
Thank you very much, sir. Thank you, Dr. Arilal, as well as Dr. Vijay Yadavji, for giving me this opportunity and to interact in this forum of NISTI. I am thankful to all participants who spared his time to join this online lecture, Smart Textile for Emerging Business Opportunities. Although it is very big topic, very big umbrella, but I will try to cover as much as possible during this span of almost 1 hour. When we talk about smart textile, 3 words comes in our mind. First is sense, another is react, and third is adopt. So whole smart textile story that will revolve around these 3 words: sense, react, and adopt. If you will see the definitions of smart textile, you will find hardly a standard definition of smart textile. Time to time, different authors, different academicians, different researchers, they coin different definitions of smart textiles. Out of them, I will focus on 2, which are most popular. Smart textiles are integrated form of textile, computation facilities, and electricity connectivity. Another definition is the smart textile are materials structure which can sense and react to external stimuli like heat, pH, resistance, temperature, etc. So out of these two definitions, we have also tried to formulate one definition that I will discuss later on during this presentation. Smart textile are textile materials that responds automatically to changing environment stimuli. Suppose a textile is not responding, it can only sense, then again it will come under the category of smart textiles, because there are 3 basic categories or classes of smart textiles. But here these are the functions, like if a textile responds start automatically without assistance, then it will be a smart textile. If surrounding conditions like are driving forces like light, dark, hot, cold environment, if a textile is able to react according to these surrounding conditions, then that textile definitely come under the category of smart textile. This is the informal classification of smart textile, because there is no authority or body who have recognized or authenticated the classification of smart textile, but still worldwide this classification is accepted by the both communities, scientists as well as academicians. So passive smart textile are basically the sensors which can only sense the environment, but they can't react. Second category, active smart textile, they can sense and react to the environment. And third is very smart textile or ultra smart textile, they can sense, react, and adopt themselves according to the environmental stimuli like temperature, pressure, pH, hot, cold, whatever it is. These are some data which I collected from different sources, like a global e-textile and smart clothing market, as Dr. Lal was saying during the preface session. This sector, the whole smart textile sector is registering around 20% CAGR. If you will start from 2020 and when you will reach at 2028, then the market has been that will increase from 1,725.2 million US dollar to 18.9 million US dollar. So this will encounter a CAGR of around 20%. If you will see the reason why smart textile market, then you will find, of course, this North America that is registering a very healthy growth. After that, the European Union, then Asia Pacific, and then rest of the world. If you will see the smart textile market segment, which segment is registering how much growth and what are the opportunity in different sectors, then you will find healthcare sector that is doing all very well. Second is the military and defense and military segment, then entertainment sector, automotive sector, fitness, and others. So these are the different sectors. And the, health and fitness, this is very lucrative segment nowadays. And different textile manufacturers, they are willing to enter in this field also. And that may be a good decision. Textile manufacturing processes are quite fast. If you will see in terms of data, then you will find the fashion and entertainment sector. This is another very enthusiastic sector, very optimistic sector, where the growth of smart textile is too much. Second one is medical, defense, military, sports, fitness, transportation, architecture. All these sectors are just following the fashion, entertainment, and the medical, defense, these three sectors. If you will see the history of a smart textile, then again, you will not find a very systematic or chronicle history of a smart textile that is written by any author in very authentic way. But whatever information is scattered here and there, I try to collect. And the electricity-induced corset and belts were first developed in 1850s. You can say just 170 years back. After that, the wearable computer was dreamed, not manufactured. That was dreamed in 1955 by Edward Thorpe and Claude Shannon. And what was the major problem? Because electronics and textile did not integrate well. And there was not enough opportunity or facilities to integrate both these segments. After that, the integration was started in 1990. Thereafter, the Georgia Tech Institute of USA, they developed a wearable motherboard in 1996, and they provided a platform for computation on textile surfaces. So that was a big breakthrough of that time. After that, the Massachusetts Institute of Technology, they developed the embroidered keypad in 1997 and 1998. So these two inventions were very big invention of that time, and they basically motivated the whole world that this is also possible. So after that, in year 2K, the fiber level electronics were started, and various countries, they start to pour enough money, and they sanctioned very big research projects for fibertronics. After that, the woven textile inverter circuits using flexible strips with simple and thin films, that also came in picture, and that motivated to so many researchers, academic institutes, as well as laboratories also. You will see various segments, phototronic, medical textile, controlled drug delivery system, wearable electronics. These are some majorly discussed segments. But apart from these segments, there are other segments also. If you will see the three functions of smart textile, then you will find the energy harvesting. That is the first function of a smart textile. Any kind of system which have the ability to actuate and respond accordingly, it requires some energy. So this system must have its own power system, power generating system. So energy harvesting is the first feature which is essential for smart textile. Then second one is, after harvesting, energy storage, and then third is energy utilization. Fabrication of a smart textile. How can we fabricate? Suppose here some budding entrepreneurs or some established industrial stalwarts hearing this talk. Then these are 4 stages. We can enter at any one of the stage, and we can go ahead. Like at polymer stage, by introducing functional monomer or introducing additive to make functional fiber forming polymer. If we are able to do that, then we can say we have already completed one step ahead towards smart textile. Second stage, textile fiber that have additional functions and we can introduce these additional function in terms of increasing the conductivity, because otherwise the all textile fibers, most of the textile fibers are very bad conductor of electricity. So if we are able to introduce the electrical conductivity or optical conductivity to textile fiber, we can extract so many functions only by introducing these two attributes in textile fibers. Third one is yarn stage. By integration of conductive or self-releasing component at yarn stage to integrate with functionality, then that will be another stage or another step to move towards the smart textile. Fourth one is fabric stage. The attachment of commercial off-the-shelf components such as integrated circuits or light-emitting diodes to the textile after fabrication, then definitely the textile will convert from traditional textile to smart textile. Another approach is hybrid approach. In that approach, we have to combine both traditional and smart functionalities at a single platform to convert that traditional textile into a smart textile. How can we convert the traditional yarn to a conductive yarn, which are essential to manufacture smart textile? So we can start from metallize the textile fiber by introducing carbon nanotube or metal powder at the time of fiber manufacturing with the dough or with the polymer. Then we can use the metallic fiber or filament. We can develop or we can manufacture the metallic fiber or metallic filament, and then use metallic wires for embroidery, and then stranding, wrapping, twisting, or metallic wire on the surface of traditional wire. So in this, these are the four components or four ways by which we can produce a conductive yarn, which is very essential to manufacture smart textiles. Now, integration with traditional textile. There are different sectors because smart textile cannot manufacture in isolation. This is a fact, and we have to accept this fact also. We have to integrate with other fields also. If we want to really develop an effective smart textile and a cost-effective smart textile, it is only possible when we will work together with telecommunication sector. We are ready to work with material scientists, artificial intelligence, biotechnology, electronics people, pharmacology people, pharmaceutics people, cosmetic science, machine learning, polymer science. These are the areas by introducing or by integrating with these areas, we can develop different type of smart textiles successfully. This is the work which is conducted in our laboratory. One of our PhD students work on this sector in this 3D orthogonal fabrics for electromagnetic shielding. We introduced copper monofilament as a conductive component of the yarn, and 300, 350, 400 tax hybrid yarns were developed, and those yarns were used as a BAFT yarn. And binder yarn, that was also a conductive yarn. And by using this design of experiment, we developed 16 different samples and we tested for electromagnetic shielding, and the results were very, you can say, motivating results. And this work has been published in Journal of Industrial Textile. After manufacturing of smart textile, this is another very important stage that we have to evaluate the smart textile. Either it is completely a smart textile or it is not a smart textile. We are just saying it is smart textile. So smart textile it means it must have some functions there, and we have to evaluate and authenticate all those functions properly. Overall performance, power management system must be there, ease of manufacturing, it must be cost effective, easy to handle, fault tolerance limit that should be there, memory storage and transmission facility must be there, sensor processing and control of output and input. These are some essential features which has to be evaluated after the smart textile manufacturing to authenticate our product as a smart textile. Then this is the hierarchy of a smart textiles. Back manager means hardware software integration to collect the and analyze the sensor data, because we have to put a sensor to sense the environmental stimuli. After that, there should be memory storage place, processor, wireless interface, and a circuit board attached in the form of a patch or signal converted from analog to digital. And this circuit board that can be attached on any kind of a dress like jacket or trouser as a small patch. Then a circuit, and this circuit can be embroidered by means of metal threads and as a interconnector. Then stretch sensor, because textiles are not a rigid material. When we will wear a shirt, when we wear a jacket, then we have to move our body parts like arms or hands, legs. So textile must be stretchable and sensor must be stretchable. And whatever gadgets we are incorporating on these textile materials, they must have some capability of stretchability. If they are completely rigid, then that kind of a smart textile cannot be a very successful smart textile. So this smart textile hierarchy is also very essential in that sense. These are 5 important functions of a smart textiles. If a smart textile has any one of them 5 functions, then we can say that is a smart textile. But its class will be different. Either it is a passive smart or active smart or very active smart. It will depend on how many functions incorporated in that particular textiles. So first one is sensing. After sensing means we will collect the data, then data processing is required. According to the data processing and data churning, then there will be a decision, and that decision has to be actuated by means of an actuator. And then storage, and then finally the communication means the final decision. These are the sensors which are successfully incorporated on textile surfaces at different part of the world by different laboratories to achieve different type of functions. Like the sensors are the components that transform one type of signal into another type of signal. We can start from thermal sensor, because these thermal sensors are quite important to convert a temperature sensitive textile. It detects the thermal change. A transmitter that changes resistance due to thermal change, or stimuli responsive hydrogels that swell in response to a thermal change, that works as a thermal sensors. And these type of thermal sensors are incorporated on textile surfaces. Then sound sensors. These sensors are used to convert the sound into an electrical signal, and piezoelectric materials are the example of using as a material for sound sensor. Then pressure sensor. Pressure sensors are used to convert a pressure to an electrical signal. And the basis of this conversion is based on simple operations such as the opening or closing a circuit. And it is more sophisticated form of a capacitor or a piezoelectric crystal line. The next one is chemical sensor. Chemical sensors are able to detect the presence and or concentration of chemical or chemicals. Next one is a light sensor. Light sensors are able to convert light energy into voltage output, and photoresistors are the example of light sensors. Humidity sensors. Humidity sensors are used to measure the absolute or relative humidity at any textile surfaces. And it is required and it is necessary to sense the actual intensity or actual amount of humidity which is present on that particular surface. The capacitive devices that changes the dielectric properties with the absorption of moistures are the example of humidity sensors. Then strain sensors. Strain sensors are used to convert the strain energy into an electrical signal. And these strain sensors work on based on semiconducting materials and strain sensing structures. Piezoelectric materials are also used here to form a strain sensor. Then biosensors. This is very new member of this family, biosensor. Biosensor consists biological elements as primary sensing element, and these elements responds with a property which change to an input analyte. like we have to check the glucose level in any person's blood, then we require biosensor, and this biosensor must act on textile surface, and it should be able to analyze sweat, not the blood, because sensor we are not injecting any needle inside the body of the bearer. We have to just analyze the sweat of that person. This is just a simple example of a jacket where different gadgets are there. Actuator is there. A flexible antenna is also patched on the front portion of this jacket. Then interconnection means circuits are there. Data processing unit is there. The sensor on sleeve area is there, and there will be a power generating and power supply system. Now, this is the second function of a smart textile: data processing. It is required in case of a smart textile, not in case of passive smart textile. It is necessary to process every collected data by suitable processor and obtain the desired output. If we don't have data processing, then there is no mean to use the sensor. The use of sensor will go in waste if we we are not able to process the collected data. The major challenge is about the data evaluation and presenting the data. After data evaluation, then it will match with the threshold limit, and the final decision, yes or no, that will come in the form of a actuator's activity. So variation of signal and analysis of signal are the main problem for data processors. The supply of required energy to processor is another challenge, because suppose a wearer has wear that particular jacket or dress for 12 hours, then with the power harvesting system or the battery which you have incorporated to support this data processing unit must able to feed or keep live that data processing unit up to that extent of time. Since the electronic components required for energy don't have sufficient fineness and flexibility, this is another challenge. If the diameter of that circuit or that wire is too high, then it will create the rigidness. So fineness is very important. If we are able to make it small, then so many problems will solve immediately, because the coarse structure that creates a lot of rigidness, and fine structure that develop the flexibility. So textile structures require flexibility, not rigidness. Electronic components have problem of its size and stiffness. And these are some issues with the data processing. Now, actuators. This is third function of a smart textile. Actuators perform action as per signal received from sensors, and then it receives electrical input, or it takes physical action accordingly. And the shape memory materials are the best example of actuator, which are incorporated successfully in various types of smart textile for different functions. Here we can see the function of actuators. This is a micro capsule where the core part is different and its sheath is different. Core part is some active material is there. If you will heat, the diameter of this capsule has been reduced, and the pH also increased from 4 to 7. When you will again cool it, the diameter or size of this capsule will enhance again. When you will again heat it and pH will reach up to 4, then it will again reduce its size. So this is the example of actuator. Now the storage. Storage, we can see here, the storage of energy or informations are very essential for a smart textile. Energy storage is needed to trigger the function, and it is required to compute and communicate the information from a textile surface to a control unit. Then integration of energy source and storage, that is also required, and this integration must be very effective and sophisticated. To inject or emit the drugs, in case of a controlled drug delivery system, we require a storage system, we require a trigger system. So as per the need of the human body, the actuator must release the controlled amount of drug at particular time. So that type of medical textile will come under the category of ultra smart or very active textile. So energy sources, what are the energy sources? Energy sources are our body temperature, mechanical movement, because all the time when we are not sleeping, then our body makes some movement. So that those type of movements can convert into electrical energy, and that electrical energy can save on battery, which is integrated with that particular textile. Uh, yes. Uh, these are major smart textile which I have put here, like a temperature controlled smart textile, color changing smart textile, safe memory based smart textile, waterproof breathable fabrics. Somebody can ask a question: waterproof? How waterproof breathable fabric is a smart textile? I will explain this question later on during this presentation. E-textile, everybody agree e-textile is are a smart textile. But waterproof breathable fabrics are also smart textiles. Suppose I incorporate a safe memory material to block the force of a textile surface, but it is a temperature sensitive material. So as the temperature will increase, the safe memory material will shrink and pores will open. And the moisture vapor, which is accumulated in the inner side of that particular surface, that will go out. And as the moisture vapor will transmitted through the material, then again temperature will go down and pores will close. So in this way, these type of waterproof breathable fabrics behaves as an active smart textile. Now, this is another function or fourth function, you can say the communication. These devices are mounted between two different elements of the garment. We can't mount these communication devices just over the surface of that jacket or trouser or shirt. The optical fibers or conductive fine wires weave into the fabric and they form the woven antenna. In this way, we can communicate through that woven antenna from one place to another place. A communication protocol is needed to communicate with the bearer. Philips, a research laboratory of Netherlands, they developed a driver suit with wireless data communication to measure the driving comfort. Suppose a driver is driving a truck for a long distance and he's performing his duty since last 6 or 8 hours, then we have to measure the comfort level of that driver for a safe driving. So what measurement must be there? The heat comfort, how much heat comfort is there, how much moisture vapor concentration is there, and what is the mood of that person. So that can also be measured, and that is also essential for better and safer driving also. If you will see the safe memory materials in smart textile, then we can say these materials are capable to remember its original shape. This is the basic function of safe memory materials. When we introduce safe memory material in smart textile in different way, then it creates the smartness in textiles, and that conventional textile converted to smart textile. It returns to its original shape after actuation by temperature, stress, sound, electrical, and pH, different type of stimuli. It will depend on the type of safe memory material. What is the actuator for that particular safe memory material? Alloys, gels, ceramics, polymers. These are some examples of safe memory material. These safe memory materials actuate, they must actuate close to our body temperature. If they are actuating at 130 degrees centigrade, then they are not useful to be used as a safe memory material for a smart textile development. They must actuate in between 30 to 40 or 30 to 50 degrees centigrade. So this is the temperature. If they are actuating between 20 to 40 degrees centigrade, then we can say they are very good for to be used as a safe memory material for smart textile manufacturing. This is the nickel titanium alloy safe memory material. Just an example. These materials have elasticity and hardness must actuate in narrow temperature slate. Then second function is nickel titanium alloy. They can very easily incorporate on textile surface for measuring the temperature regulation of a particular wearer's body. Then these nickel titanium alloy, same memory material, works like a spring on textile for enhanced protection. And nickel titanium ratio, if we are changing the nickel or titanium ratio, we can play with the property of that safe memory material. Suppose we want to reduce its actuating temperature, we want to increase the actuating temperature, then we have to change the ratio of nickel and titanium. There is a company in Italy that is Corpo Nove. They developed a T-shirt, and that T-shirt has a property to shorten its sleeve when the temperature goes high. So when the sleeve will shorten, then it will provide a passage to transmit the moisture vapors which are accumulated on close to our skin. Now, these are some example of safe memory polymers. These polymers have elasticity. They have a different refractive index. They have a volume below and above the TG. When the glass transition temperature is very close to the room temperature, then those type of polymers are very successful safe memory polymer, and they can be used in the form of gel. They can be used in the form of strip, in different packets, or in the form of layers. These safe memory polymers are incorporated between two layers to regulate the transmission properties of that particular textile item. They actuate by increase the temperature. When temperature increase, it expands its porous and porous structure and allow the expansion of body heat. And crystalline trans isoprene rubber is one example of safe memory polymer. Here we can see some other examples of or other application of this safe memory polymer for medical application. Like self-tangled surgical threads are designed for endoscopic surgery, and implants that are small in normal ambient conditions are designed for the use of endoscopic surgery. Some safe memory materials used to perform operations with a small incision, shortening the healing time and risk of infection. Benzoxazine based copolymers are the example of such type of safe memory polymers. Safe memory textiles can also be used for aesthetic and decorative purposes. Now, electricity harvesting textile. This is another kind of smart textile. Electricity is needed to functionalize the electronic devices which you have already incorporated on textile surfaces. This electricity can be converted from light, thermal, and mechanical type of energy. Sunlight, ambient temperature, gradient, and human motion abundant sources are the sources of energy, which can also be used for energy harvesting. The conversion of light into electricity performed by photovoltaic effect, and such type of smart textiles are called as photovoltaic textiles. Now, the smart textiles for photovoltaic application, we can take the example. The electrons in the valence bond, they absorb light energy. Suppose one atom is there, another atom is there. There is a bond between these two atoms. So some bonds are capable to absorb that light energy. And after absorbing that light energy, they get excited and the jump to the conduction band and to become free. Then the excited electrons diffuse to reach a junction where they are transported into different materials by a built-in potential to produce electric current. These are two different examples, like a dye-sensitized solar cells, DSCCs, and polymer solar cells. They are used to convert the light energy into electrical energy. Solar cells onto fiber surface, we have to mount, we have to coat and woven into the photovoltaic textiles. So here you can say this is a fiber which is coated, and this is another fiber which is coated in different way. So both cathode and anode are developed on the same surface of the fiber. And when these fibers are woven in this form, then this kind of textiles is called as photovoltaic textile, and these textiles are used to convert light energy into electrical energy. This is the way, like suppose this is light, this incident on this surface. This is anti-reflective film, which will absorb as much as possible light. And after that, this is the negative type semiconductor. This is the interface of negative positive semiconductor. This is positive type semiconductor. When this light will incident on that surface and that will absorb by the bond, and these free electrons and positive ions will excite by means of this energy, and this then the electrons will move from one surface to another surface, and in this way the electrode the current will flow between these two electrodes, and that current will store in a battery. So in this way, these photovoltaic textile works, and these kind of photovoltaic textiles are becoming very popular. And the curtains, particularly the curtains where the direct sunlight comes, so those type of curtains can be used as a energy harvesting textile for photovoltaic purposes. Fiber-shaped solar cells. Fiber-shaped solar cells are available either in twisted or in coaxial structure. Twisted structures, photovoltaic materials are coated onto a fiber electrode and then twisted, then another fiber electrode. Coaxial structures, a very thin layer of electrode material which is deposited directly on fiber surface to form a coated electrode with a photovoltaic material. The twisted structures are more compatible with continuous production in comparison of coaxial structure, because they are more robust in comparison of coaxial structure. This one we can see here in very easy way. There are some metallic wires which can also be used for photovoltaic applications. So metal wires, they works as fiber electrodes, and high electrical conductivity they have, and they have low cost also. So metal wires are very good example of converting or to use as a cathode or anode in case of a photovoltaic textile. Stainless steel wire coated with TiO2 nanoparticle that will work as an electrode, and then twisted with a platinum wire as a counter electrode. If it is you are using as a cathode, then another will be anode. So the coated TiO2 nano, then there is an issue with such kind of photovoltaics. Like coated TiO2 nanoparticle peel off, that creates crack and reduce the efficiency due to deformation in textile. When you will use these type of wires as a bark or baft or as a embroidery thread, and when the wearer will make body movement, then the bending will take place, and due to bending, the TiO2 nanoparticle coating will peel off and cracks will generate. When cracks will generate, the efficiency of conversion of light into electrical energy, that will reduce drastically. So this is one example where the fiber is coated perfectly to make a fiber battery. Carbon nanotube and graphene, they can also be used on textile to convert into a smart textile. Graphene can be introduced into the fiber that simultaneously display high electrical conductivity, tensile strength, and high electrocatalytic activity also. One of our colleague, Dr. Mehti and Dr. Shukriyo, both are working on graphene nowadays, and they are extracting some very good property of this graphene. So titanium wire as a working electrode and coating platinum nanoparticles are used on graphene hybrid fiber as a count to manufacture the counter electrode also. Textile shaped solar cells can be developed for home textile to convert the light energy into electrical energy. So photovoltaic textile, they can be manufactured by weaving. So woven fiber shaped solar cells directly fabricated from textile substrates based on polymer fibers. So this poly-1,3-ethylene dioxythiophene and polystyrene sulfonate, PE-DOT and PSS, a photovoltaic layer and a transparent lithium aluminum electrode were subsequently deposited on a silver modified textile to form the photovoltaic textiles. So these type of developments are already registered, and so many laboratories are working to make it cost effective. This is another kind of smart textile which is also possible, and demand of such type of textile as a in the internet entertainment sector and in fashion sector is continuously increasing day by day. The segment is color changing or chameleon textiles. What is required there? Basically, it require the actuator. Actuator may be photochromic, means light affected. They may be thermochromic, heat affected, electrochromic, electrical energy based, solvent chromic, solution affected, holochromic, pH affected, trivochromic means friction affected, and mechanochromic means pressure affected. So such kind of actuators are required there to change the color of a surface from one color to another color as a function of time, temperature, electrical energy, solution, pH, etc. The external stimuli to actuate these types of actuators are light, heat, pH, solution, friction, pressure, all those type of things. Then color change due to the alteration in electron density or molecular structure due to the external stimuli. So when external stimuli will actuate the actuator, the electron concentration will change from one place to another place, and the that particular surface will change its color. The fundamental of visible light region is always with us, because as you will reduce the size of any material, the material will change its color also. Because at 400 nanometer, violet light is there. At 700 nanometer, red is there. So as you will change the refractive index of a material, and refractive index will change by the concentration of electron cloud or electrons at that particular moment in that particular atom. So in this way, this type of color changing or chameleon textiles are developed to form a class of smart textiles. So chromic effect that may be at polymer stage, that may be at fiber stage, and that can be created by fiber dye, because some dye stuff is also available which have the chameleonic functionality. Yarn that can be achieved by yarn coating, by fiber dye, fabric dyeing, and by inkjet printing. Nowadays, inkjet printing is becoming very popular because the versatility of this technique. Because nowadays these inkjet printers are so too much versatile, and any kind of material, means a wide range of material can be printed on textile surfaces successfully. Chameleon smart textiles means thermochromic dye stuff containing fibers shortens fabric pores get enlarged to trap the large amount of air, and consequently the body temperature decreases. At low temperature, the fibers are elongated, the pores are closed, and the fabric maintains the body temperature. The thermochromic dye stuff smart textiles are used for firefighters. Suppose the temperature of surrounding of a firefighter is increasing as a fraction of time, and the person is performing his duty, he don't know how much temperature has been increased. So before just reaching a threshold limit, there should be an alarming system on the dress of that material. That alarm should warn to the firefighter, now you have to leave this place, or you have to take some other curative action or protective action. So in this way, the chameleon smart textile can work. The chameleon smart textile, there will be another application when we are able to integrate such type of textile materials with some biosensors. If those biosensors actuate with these type of materials, then these type of textiles are able to indicate or characterize or to indicate the presence of a different a category of virus on that particular surface. So suppose a surface, or suppose a mask surface is infected by a particular class of the virus, then the color of that particular mask will change. So that is also possible. So indirectly changes the heat absorbing property of a textile material, and due to the change in heat energy, the color of the material that get changed. So that is a class of chameleon smart textile. If you will see the phase change materials, you can say the first generation of smart textiles were developed by using the phase change material as a temperature holding material or temperature storing material. So during phase change, these materials absorbs and holds the large amount of heat energy, but temperature remains constant. So that depends on basically the latent heat of those materials. If those materials have a very high latent heat, and that temperature should be very close to the room temperature or our surrounding temperature, then those type of materials works as a phase change material or effective phase change materials. During cooling, the stored heat is released when material changes its phase from liquid to solid. By using two or more phase change materials together, the phase change temperature range can be engineered. Suppose we want to enhance the range of the phase change material, only the wax, natural wax or synthetic wax will not work there. So we have to make blend two or three different type of phase change material. Then we can engineer a range of that actuating temperature. The degree of heat storage and release depends on type of material used, its thermal capacity and amount of application or the place of application. For effective application, the phase change temperature and the actual use temperature must be very close with each other. Otherwise, the phase change material will not work and we will not get the exact benefit from those type of materials. These PCMs can be applied to textile materials by microinserts and microencapsulation technique, which is very effective technique till date. These capsules are added to the fibers surfaces, added to non-woven surfaces, or coated on different textile surfaces. When wearer move from warm to cold environment or from warm indoor environment to a cold outdoor environment, the PCM-based garment showed heating effect on average 12 to 15 minutes, depending on the phase changing material content and outdoor conditions. So this is another challenge. We want to increase this time spent, 12 to 15 minutes. It must be up to 30 minutes. So a person, suppose the person is working in extremely adverse environment, he must have a production of 30 minutes. This is the mechanism of phase change material, which is shown here. Basically, the phase change material, they have transitions. They have different transitions. So when we conduct the isothermal study of those materials, we are able to capture or record the exact amount of latent heat at that particular temperature. And it should be as high as possible to enhance that, that effective temperature, effective time for that particular phase change material. Phase change materials you can incorporate on different textile surfaces, like a microencapsulated PCM on yarn, non-woven or fabric surface. During cooling, the heat release material from liquid to material will change from liquid to solid. PCM operate temperature engineered by using two or more PCM. Heat amount of PCM, heat capacity of PCM. PCM-based hospital mattresses, pillows, bed sheets, surgical gowns. These are some other example of phase change material, particularly in healthcare sector, to make the healthcare sector more comfortable, more effective also. Here, why I place this slide here, because this is a very important sector of smart textile. So global advanced phase change materials market by region wise, and 2020 to 2027, it is expected that you can see clearly that in all regions, the application of phase change material is increasing day by day. If you will see this wearable smart electronic textile, then you will see that to make human life more reliable, healthy, and comfortable. This is the purpose of using electronics in textile. The purpose is not to make the person lazy or dependent on others, basically to enhance the quality of life. Temperature change, light, moisture, such as environmental stimuli can detect and to react these stimuli and can change itself according to external conditions, store the data, application of stored data, and make the effective communication ultimately. So these are the functions of an effective electronic textile or e-smart textile. E-smart textile supports the vital activities of human beings such as sensation, movement, communication, taking action, and adapting the environmental stimuli or conditions at that particular moment. This is the basic component of e-smart textile. First, the advantages of e-textile is easy to form, but easy and difficult to wear. These are easy to form, but difficult to wear. There are four challenges with these e-textile. First challenge is large and rigid electronic components have to be incorporated with textile. When you will incorporate these gadgets with textile, it reduces the comfort index, and that textile becomes very difficult to wash. Second challenge, production of electronic components using textile materials, textronics. This is another word which was coined 10 years back. Integration of textronic with the conventional type of textiles is another issue, because you can't shui the textile, these electronic gadgets on textile surface. These gadgets should be flexible enough. That's why government of India has given a very big project to IIT Kanpur to develop flexi electronics with the name of flexi. Third challenge is limited number of textronic integration is available, and different laboratories are trying to enhance this number. The e-textile are produced by using electronic functioning fibers also, and this branch or this sector or this segment is known as fibertronics. These are the basic components of e-textile, like lightweight energy storage system must be there, sensors should be there, and then actuators should be there. So composite fiber, they can also be used. Geometric design, we can change as per our requirement. And you can say the printing of these circuit on textile surfaces is always remain very big issue. But after the invention of 3D printing machines and very effective robotic arms, these challenges has been reduced up to major extent. This I have already discussed. Sensors continuously monitoring breathing, heart rate, body temperature, and these sensors provide the mobility to patients, sports person, and disabled persons. Sensors can sense the presence of toxic gases, chemicals, pathogens to assist the pioneers, hazardous workers. The Siberia Smart Coverall with wearable technology is designed to burn in polar areas. The garment displaying health data also included global positioning system, GPS system, for the use in the event of a loss, and GSM module that can automatically send the coordinates and health information to a predetermined number in the event of abnormal condition. And such type of devices are very useful for military purposes. Smart textile for emerging business opportunities. You can say these textiles are becoming popular day by day. People are trying, and these type of textile has been manufactured, but some issues are there, because effective textile must be washable, it must be wearable, it must be comfortable. When the textile will solve all these issues, then that type of textile will become a popular smart textile. So laser printed, waterproof, and stretchable e-textiles, they are also developed. The technology enables graphene super capacitors as a powerful, long-lasting energy storage device, which are combined with solar or other sources of energy harvesting, laser printed directly onto the textiles. So RMIT University in Melbourne, Australia, they developed this kind of stretchable e-textile, which is shown here. Conductive textile, because in case of electronic textile or e-textile, conductivity is the major function, or you can say the primary function. Without conductivity, we can't develop any effective e-textile. So a conductive textile consists of fabric which is made from strands of a metal that are woven, blended, or coated. Silver, titanium, gold, nickel, carbon are utilized to convert non-conductive textile into conductive textile. The primary function of conductive textile is controlling the static energy and protecting from the electromagnetic interference. These conductive textile provides electromagnetic shielding and conductivity in some selected applications or some selected areas. These are some selected applications of a smart textile in healthcare sector. Knitted or woven fabrics are being used to assist in life-threatening condition of a heart and vascular system. Smart textile is developed as a cardiac support device, CSD, which intended to reduce the cases of heart failure. This device consists a mesh-like bar-plated structure by multi-filament polyester textured yarns to keep the heart in shape. When the heart start to enlarge, then the blood pressure and all such type of heart failure problems becomes very common. Graphene-based smart textile. Graphene is another material which has gained popularity in last 1 decade due to its very smart applications. Extensive application in wearable technology of graphene has been registered in last 1 decade. Graphene covered fabric preserve the human body temperature and allow an even body temperature during physical activity. Means homogeneous distribution of temperature from shoulder to our feet. So Director Plus and Colmar, these are two companies that produce graphene-based jacket with a trade name of Sky Jacket. Intelligent bra. This textile has a function of sensing. So heart activity can be sensed continuously, and it has a data processing unit to sense the emotional mood of the wearer. Then it has a signal unit to combat the overheating signal. And after that, it will respond and it will give a signal to smartphone. After that, a corrective action can take and flash a warning action or warning alarm on that particular smartphone, and the action will take in terms of balanced diet or some drug to control the heart activity immediately at that particular time. But this such type of devices or intelligent bra are very effective for diabetic patients, particularly during the time of sleep. Smart film fabric. DuPont developed with the name of Intexa. This is a revolutionary electronic ink and film that seamlessly transform the fabric into smart clothing for multiple applications. The technology offers both ease of integration as well as ease of design. It is currently leveraged for 3 applications: fitness, heat, and seal. A thin layer of carbon or silver serves as a sensor, sensing electrical signals, while a conductor made of a layer of silver, it transmits current throughout the textile from one end to another end. Other films are integrated onto the textiles to protect the structure from water and additional exposure. The heat application utilizes the battery power technology, and that includes a resistor, a thin layer of carbon that radiates heat, and conductor and thin layer silver that transmit the heat from the surface that can capture by another device. The textile shaped lithium ion batteries. Because when we are developing e-textile, we are developing active smart textile, we require a power system, power backup system, which must remain integrated with that particular textile. So these battery textiles can also be made directly from textile electrodes. Polymer textile coated with conductive material like nickel was coated on polyester textile as to convert it as an electrode, which is followed by deposition of a slurry composed of active materials like Denka Black, polyurethane binder, commercial LiFePO4 and Li4TI5O12 were used for the cathode and anode respectively. The battery textile worked in a voltage window of 0.6 to 2.4 volt. This is not useful at very high voltage. Voltage range is 0.6 to 2.4 volt, which is demonstrated a specific capacity of 100 mAh at 0.5 degrees centigrade. Compared with the insulating polymer textile that require further deposition of conductive layers, conductive textiles such as carbon cloths are prevalent. A variety of active materials such as ZnCO2O4 nanowire arrays with a name of WO3 at the rate of SnO2, core cell nanowire arrays, Fe2N nanoparticles, and aligned Ca2Ge 7016 nanowire arrays were deposited on these conductive textiles. In this way, these textile-shaped lithium-ion batteries are possible, but the voltage window is very less. So different researchers, different companies, they are trying to enhance this voltage window. These are the examples of some these lithium-ion batteries which are based on ceramic fibers textile structures. These are some fiber-safe supercapacitors which are useful in this way. These are some medical applications of smart textile. These are some physiological measurements which are possible by textile integrated sensors. Uh, Signal sources are also there, and typical sensor placement means where we have to place. I'm just reading one example like breathing pattern. We want to measure the breathing pattern of a patient. Then piezo sensitive stretchable sensors are required there, and signal sources expansion and contraction of that rib cage during the breathing. And these type of sensor and these type of smart textile can be placed on thoracic or abdominal region to monitor the patient's breathing pattern regularly. So this is a huge list. We can measure the blood pressure, we can measure the body movement pressure, electrodermal activities, different type of activities are possible to measure this way. This is another example, that is a blood oxygen saturation level, and this is possible by means of this device, which is very common nowadays. This is called as oximeter. So the concept is very simple. Like now, body movement. Body movement can also be monitored by means of these smart textiles. Monitoring body movement can give an indication of general activity, which may be useful in monitoring the well-being of isolated individuals or motivating patients to maintain the daily activity level in case of obesity or cardiovascular diseases. So body movement. Suppose they are doing some yogas, some asanas, then how much these yogas and asanas are effective, and what are the frequency of those activities, that those type of activities will measure continuously, and we can communicate from one place to another place effectively and immediately. So measuring is specific movement motions have application in rehabilitation therapy also. Monitoring characteristics of body's movement is also useful in assessing conditions affecting motor skills as well as Parkinson's disease. There are two main approaches in smart garments for monitoring biomechanics. One area is the use of internal sensor together and advanced algorithms, and other area is the development of textile based sensors. I'm not discussing in detail. Now this is the electrodermal activities. This is related to the measurement of electrical conductivity of the skin, especially as an indicator of someone's emotional response. So is it possible to measure some emotional response of a wearer? Yes, it is possible. The emotional reactions varies from with variation in the sweat gland activity on the palm of the hand and the sole of the feet. The baseline level of skin conductance varies from person to person and depends on both patient's physiological state and autonomic regulation. This baseline varies slowly over time, which indicates the general activity of perspiratory glands that may be affected by factors such as the temperature. A faster phasic change or peak in skin conductance can occur as a result of a specific stimulus or event. This response appears between 1.5 to 6.5 seconds after the stimulus. Electrodermal activity EDA is generally measured by the placing AGCL electrode on the first and second finger of either one or both hands. One electrode emits an electrical signal, whilst the other primarily acts as a receiver. Thus, a circuit is established, and the electrodermal activities are registered and measured and recorded and communicate from these type of textile from one place to another place, from one wearer to another. Two prototypes were developed. The first was based on the Kapton copper foil, and the second was hairnet structure or standard AGCL electrode embroidered on the surface of a textile. The European Union, SHITE and the Monocra projects have also developed garments as a part of their system to support the diagnosis and treatment of bipolar disorder patients. The Monorca project has shown the integration of the sensor system in a shoe or sock as a promising approach, because the sock will always remain in the contact of foot. So EDA peaks at the foot occurred around 0.5 seconds later than the ectodisciplinar's EDA peak that appears on the hand. The context of the user, such as the outside temperature and clothing, needs to be taken into account when measuring the analyzing EDA traces. In the SAIC project, the hands and feet have been used for the measurement purposes. These are some
Dr. Mukesh, how much is still left?
Can I finish, sir, now? I will finish, no problem.
I think because it is more than an hour now, and
Okay.
Some messages I am getting from the audience.
Okay. So the composition of body fluids and sweat analysis is also possible by using these type of textiles. And the sweat rate sensor developed at the University of Pisa during the BioTex project, and humidity sensor integrated onto textile pockets of the sensing devices at different distances from the skin. These are some woven batteries which are developed by Montreal in Canada, a Polytechnic School of Montreal. A solid polyethylene oxide electrolyte between lithium iron phosphate cathode and lithium titanate anode. This is another project which is continuing in our laboratory, in which we are developing the bacterial cellulose based control drug delivery system to treat the different kind of wound in a controlled fashion. These are some challenges again for a smart textile development. Means smart textile leaves a rough surface. Keyboard, suppose we are developing a keyboard, then it must pack with powerful waterproof clothing. Mechanical environment means high bending rigidity leaves mechanical field, means reduces our freedom. Poor versatility. These two gadgets are developed. One is ICD textile, and which is developed by Philips, and this is a keyboard which is developed by this. Now, product development and commercialization. The lack of integration between textile and electronics field integration, the microchip and computer system, while textile capable to bear washing issues. The multidisciplinary team is required, means textile scientists, polymer chemists, physicists, bioengineers, software engineers, consumer specialists, a fashion designer. Then we can only develop such type of textile. And the high cost is another issue to get it commercialized and popularized. Power supply to smart textile, I have developed or discussed already. This is a very attractive illuminative woven electronics, which is developed by the Philips laboratories in Netherlands. So now I am on conclusion. India as a market has huge possibility to start business for a long-term goal. Smart textile researchers are confined to development in new materials, nanotechnology, and miniature electronics and wearable computers. Smart textile wearers compromise with comfort, but it's not. Durability of smart textile did not tested perfectly. Every existing traditional textile industry must start a little product development in the smart textile area. Multidisciplinary efforts are essential for product development in this sector. So these are some opportunities, threats, challenges in the sector of smart textile. So this is all about from my side. Lal sir?
Yes, I got it. Dr. Yadav, you are taking question answers?
Yes. Thank you, Mr. Mukesh, Professor Mukesh, for a wonderful talk. And I think it has been very exhaustive, particularly interesting to the students, I would say. And it is resonating in the form of certain questions also, which I would, with the permission of Dr. Lal, I would like to spell out the questions. So we have Mr. Shailesh Kaushik. He has put 3 questions. So I ask Shailesh ji to please unmute, and you can take your questions one by one. And I would request if you can just have around 2 or 3 minutes. Over to Mr. Shailesh.
First of all, congratulations to Professor Mukesh for such an lucid and exhaustive talk. My questions are already there in the chat box. You can take it from there. Basically, one was about the graphene, which he has already attended. The other was about the washing fastness. And third one was about that how this phase changing material can be, or this shear changing material, has it been commercially used in bulletproof jackets? These are my three questions.
Sir, I'm taking your third question first. The application of phase change material as a protective element, or in case of a bulletproof jacket. Basically, in case of bulletproof jackets, the non-Newtonian floats are used. If those non-Newtonian floats have their thermal transitions close to the room temperature, then those type of non-Newtonian float will serve both purpose. Means they will provide protection against bullet as well as thermal transitions. Means they will save to the wearer from hot and cold. So it will depend on the nature and engineering of that non-Newtonian float. Because I didn't cover that part of the bulletproof jacket, because that is another very big segment, and a separate lecture is required to cover the bulletproof or that kind of protective garments or protective jackets. Both materials are different. Phase change materials they have their transitions very close to the room temperature or very close to the environment. But in case of non-Newtonian float, the transition is not important. Protection is important. In case of phase change material, transition means comfort is important. Protection is not an issue there. So this is the answer from my side.
Thank you, sir. Thank you very much.
Thank you, Mr. Shailesh. Thank you. We have next question from Mr. Karan. He needs to understand about using the smart textiles. So I think, Mr. Karan, you can drop an email. Probably we can also share with you certain informative aspects on the smart textiles at a later. We have Dr. Nandan Kumar. He has a specific query about a product. So I'm just unmuting Nandan Kumar ji. Dr. Nandan, you can unmute yourself and you can ask the question.
Thank you, sir. Thank you so much for organizing this one. Professor Mukesh, I just, you have mentioned that you have developed a fabric for protection against EMF, electromagnetic forces.
Correct.
So I just wanted to know, is there any lab in India where we can get this tested? Because, we have also developed a fabric which is 80% polyester and 20% stainless steel fiber. It's 320 GSM fabric. And we are now working on developing 150 GSM fabric. But I'm struggling to get it tested. I contacted Sasmira and they used to do it, but now I think they are moving their machine. So I think they are also not available for 2-3 months.
Okay. Sir, we have only one machine in our country to test the electromagnetic shielding, and that is available at Defense Material Stores Research and Development Establishment, DMSRD, Kanpur. Okay. So you can contact to that lab, and those people will help you definitely.
So you think they will help commercial company like ours, or we need to approach through some institute?
You can contact to their scientist. They will test your motto, for what motto you are testing, because they are DRDO people. So first they will convince by your approach, then they will help.
Okay, thank you, sir. Thank you so much for your time. Thank you, sir.
Ms. Soumya wants to know how to connect for learning more and experience such textiles. If he's around, probably he can have the question asked. Ms. Soumya, can you raise your hand?
In fact, Dr. Yadav, she wants to learn more about it, and she can connect to Dr. Mukesh. I have shared his this email.
Yes.
Without taking his permission, of course.
No problem, sir. No problem. I am always available for students.
So whatever queries people have, means members or participants have got, his email has been shared by me in the chat box. You can note it down and get connected with me.
Yeah.
If some senior person have some questions, please give him chance. Students they can send their email. I will definitely answer all questions.
Yes. Soumya has raised the hand, so I'm just unmuting. Yes, Soumya, you can ask.
Sir, actually, I am a student right now. I am pursuing a master's in fashion, textile, and innovation. So I want to learn more about these innovative fabrics and textiles.
This is very general question, Soumya. You have to read the research papers. You have to read some books because there is no book directly on smart textile, but there are some books on smart coating, smart lamination, smart fabric like that, or some means functional textiles like that. So as I have already mentioned in the beginning of this lecture, that smart textile, this is a field or this is a combination or this is an integration of different approaches at a common platform. That's why we need the assistance of different experts. If we are integrating with those experts, then the manufacturing of smart textile is possible. Only textile engineers can't do it. Only electrical engineer can't do it. Only computer engineer can't do it. So it is a integration of various approaches. And as a Indian, we are lacking in that field. We are, you can say, very poor to work as a team member. So we have to develop this habit, and we have only then we can go ahead.
Okay, sir.
Okay, Soumya, I have dropped an email ID in the chat box, so probably you can get in touch with us and we can connect you with certain articles
Okay, sir.
in further insights. Okay.
Thanks, sir. Thank you, sir.
We have Mr. Karan. I'm unmuting Karan. You can raise your query here.
Hello, sir. Good evening, sir.
Good evening. Good evening.
Yes, sir. Sir, like I'd like to know that whether Kevlar can be knitted along with polyfiber yarn, sir.
I didn't get your question. Please repeat it again.
Sir, we need to check with Kevlar along knitting with polyfiber fabric, sir. We have already developing this abrasion fabric and other this protector fabric and everything.
Mm-hmm.
We are already
You want
supplying
to you want to knit the Kevlar fiber.
Yes,
This is
sir.
your
Yes,
question?
sir. Yes, sir.
So what is the denier of that filament?
At present we are using polyester at 150 denier, sir. Kevlar we are supposed to 150 denier of polyester.
Multi-filament.
Yes, sir. Multi-filament. Yes, sir.
Okay. Okay. So if it is in lower range, basically in case of knitting, the bending
Yes, sir.
rigidity of yarn that remains always very important. If
Okay.
very heavy yarn is there, then we have to change the needle size as well as the machine type of machine. If it is
Yes,
pearl
sir.
machine or double knit or single, in this way, knitting is possible. There is no issue because
But Kevlar can be knitted, right, sir?
yes,
Okay. Okay, sir.
knitting is
Thank you,
possible. Knitting is
Okay, sir.
possible. Only you have to play little bit with your yarn.
So, we are at presently using for this abrasion fabric, we are using 20 gauge knitting machine, sir. 20 gauge.
Hmm.
But when we tried with 20 gauge for Kevlar, it is not getting knitted because since the needle are getting.
Reduce the gauge.
Okay. 14 gauge, 14 gauge and 16 gauge will try, sir.
Yes.
Thank you, sir. Thank you, sir.
फिर तो जाऊँ क्या था
Shailesh ji wants to ask again. Shailesh ji, please unmute.
नहीं सर, मेरे क्वेश्चंस हो गए.
Okay, thank you.
Dr. Yadav, there are no more questions.
Yes.
In fact, email has already been shared to participants and they can ask any queries which they have one-to-one with Dr. Mukesh. And I
Right.
would request Dr. Mukesh, to reply to their queries. And though Dr. Kuldeep Sharma has raised him, even otherwise, I wanted to invite him for his comments and views. Dr. Kuldeep Sharma, you can unmute Dr. Yadav, and he is our past chairman, and you also know Dr. Kuldeep Sharma. He is very active everywhere, even in GCTI functions, and in whole professional field.
Yeah. Kuldeep sir can unmute.
I am trying to unmute, but you have to help me out.
No, we can hear you now, sir.
Now it's okay. Can you hear me?
Yeah, we can hear you. Please go ahead.
Wonderful. Thank you, Dr. Lal, and thank you, Team NISTI. It was a wonderful presentation. And
Good evening, sir.
very good evening, Dr. Mukesh. We are very happy on this platform of NISTI to recognize your skill set and your accomplishment in the field of smart textiles in particular and textiles in general. This is a virtual program for us and we have less of interaction in person. But we at this platform wish that we could honor you with for your testimonies and credentials and the accomplishment which you have done in the industry on this platform in a possible future event, in-person event. I request Chair and the team NISTI to make a note of it and let us see how we can honor him in our coming events. Now, my observation is this, which you have all the right to correct me because it is based back in 2001 when on the same platform at NIFT in New Delhi, we had organized a conference on smart textile. It was international conference and it was supported by Textile Ministry then. Even those days in 2000, when now 2 decades have passed almost, we see the developments are still at the lab stage. We are not able to see this wearable electronics we contemplated that time, wearable electronics. We had great hope that it will come into the mass consumption of textiles for youngsters at least in the fashion area. But somehow that research or the prediction has not yet worked out. So what I would request you that if possible, you can use your expertise here in this area, why this is so dull and still we are in the lab stage, why we are not able to use this lab work or research work for the entrepreneurship in textile, because these small developments could be used for entrepreneurship in textile area, where our new generation of technocrats is looking forward to go ahead with entrepreneurship after doing the technical programs. Thank you, Dr. Mukesh Singh. Please comment and oblige us.
Thank you, sir, for your very valuable wishes and your motivating words for me. As you have rightly said, that e-textile was emerged. This word was coined in 1996 when Georgia Tech has developed the smart cert. After that, small inventions are registered, but still those issues are still there. As I have already covered during my talk, that integration of electronic gadgets with textile are not very much integrated basically. Both are different materials. The flexibility, bending rigidity, both these materials are extremely different. So we have to make those gadgets and those devices flexible. Only that in that situation, those devices successfully integrated with traditional textiles. This is first part. Second part is that if those devices are integrated, then what will happen during washing? We had to develop a separate washing system for those textiles. Another issue or another solution is that suppose we are going for washing, then all gadgets and circuits should remove and it should integrated once again in those textiles. This is third possibility. Fourth possibility is that we should develop an effective dry cleaning system for those devices or those kind of e-textiles. E-textiles are basically coming in the form of jackets, not perfectly coming in the form of shirts basically. Jackets are multi-layered fabrics. So when we are developing multi-layer fabric, then it is easy to incorporate all these type of gadgets or devices with these textiles. And another comment from my side is that when we are doing these type of researches, very big project, Department of Science and Technology has granted to IIT Kanpur, and those people are working on flexible electronics, and the name of project is Flexi. Crores of rupees has been granted to that project. And the Textile Institute or IIT Delhi Textile Department is not a part of that project. When textile development is there, electronics people are doing that work in isolation. From my understanding point of view, it is not possible to develop a effective smart textile by the efforts of only electronics people. They have to extend their hands with textile people. I'm not saying they should only talk to Professor Mukesh. They should talk to Professor Behra or Professor Istiaq or Professor Ashuri Agrawal at IIT Delhi as per their choice. But they have to work together as a team. That's why these are still there. So this is from my side. If your question is still left, I am happy to answer it again.
It was very simple, Dr. Mukesh. Whether we can think of a possibility of using it on an entrepreneur platform for the technocrats in near future.
Sir, as an entrepreneur, they can take it as a research activity first, because we have to explore the market of those products where we have to sell after manufacturing. Then what is the aesthetic appeal of those electronic textiles? If you will see the electronic textile, you will see those textiles are not wearable at all. When we talk theoretically, it is okay. Practically, those textiles are not wearable. Aesthetic appeal of those textiles is not as comparable with our traditional textiles. So we have to work on those fronts also. Then it is possible to convert those electronic textile from laboratory textile to the market textile or from a commercial textile.
Okay, thank you.
As a entrepreneur, I will suggest if any established industry is there or budding entrepreneur is there, smart textile activity must be there in their laboratory, in their development section. People are not doing anything, sir. They are simply talking. They are interested in smart textile. They want to develop a smart textile, but actually they don't want to do. They want to purchase the smart textile. They don't want to develop the smart textile. We can take the example of this bamboo tree. When you will put your bamboo tree in your garden, you will give the water, you will give the fertilizer, you will do everything. But after 1 year, the tree will just register a growth of few inches. After second year, it will register a growth of a few feet. After third year, it will make a growth of a meter. But after fourth year, it will make a growth of 100 feet. So the person who is ready to wait for fourth year will should enter in the field of smart textile.
Good.
Dr. Yadav, should we
Yes.
do the formality of
yes, I think no more questions now, and probably we had posted details of Professor Mukesh also in the chat box, so we can hope to get few queries on the mail also later on. So
I will answer all queries which I will receive in my mailbox.
Okay, thanks for your great courtesy, sir. Thank you very much. So with this, I think we have come to an end to this exciting presentation and very, very informative, I would say. And if possible, Professor Mukesh, probably you can convert it into PDF so that we can send it to the registrants.
Yes, sir. The size of this presentation, that is around 45 MB. So that is
Okay.
very big.
So maybe
I
maybe
will
we'll
I
be
will
able to
try to
reduce it. Maybe we'll
I
be able
will
to
try to compress it, and I will get success. I will definitely send to you, sir.
okay.
Otherwise, I will send it in parts.
No issue, no issue. We can do what best we can do to.
Yes, yes, no problem, no issue.
Okay, thank you, Professor Mukesh, for this talk. And I should convey my thanks to 80 plus participants also, and that shows the interest of the subject in itself. How the smart textiles is going to change the textile arena, or probably it has changed already to very great extent. So I thank you all the participants. I thank our chairman, Ministry Chairman, Dr. Ram Asre Lalji, for initiating this particular talk and breaking the ice, I would say. Uh, and this is also an announcement that we are coming with these kind of technical lectures at a periodic form. And very soon we will announce the next talk as well. So
Sir,
that's
one
thank you.
announcement from our side also. The Institute of Engineers and Textile Association of UP State is organizing the 34th National Convention of Textile Engineers on September 10th and 11th at IIT Kanpur, in association with IIT Kanpur. So those informations are available with Dr. Lal also. So I think Dr. Lal will share that information to all participants, so they can send their papers. Entrepreneurs are available. They can send their advertisements to be published in that souvenir, and they can also register to become the part of that convention. So manufacturers will be there, technocrats will be there, and different suppliers, exporters, they will also become the part of that convention.
So before we end, I would like to express my gratitude to Dr. Mukesh Singh. In fact, I should not say much about his presentation. He has a lot of commendation from the participant that he can or he could have seen in the chat box. So it was very well informed presentation, very exhaustive. Nothing was left for anybody to have a doubt on it. Everything on smart textile has been covered, right from the definitions to different type of segments of smart textiles, to actuators, to use of chemicals, fibers, yarns, and weaving techniques for making smart textiles. And at the end, that PCM, phase change material. To Dr. Kuldeep Sharma, I would like to inform that phase change materials are already commercially produced and are being used. And many type of technical textiles are being used by the army and our defense personnel. So gradually we are moving, but India, we have not been so far successful in commercial production of smart textiles, except for use of some nanotechnology and finishing techniques for functional usage and all. So thank you, Dr. Mukesh. Your presentation was very exhausting, very much learning, and we are obliged to you have given so much time, so much precious time, and so much quality time of yours for the benefit of industry participants and for the industry. Thank you so much. And we are frankly obliged of you to take out time making such a presentation and taking pains to present it here before all participants. Thank you, Dr. Mukesh, and thank you all participants. I cannot name all the participants, but the people like Dr. Nandan Kumar, Dr. Ajay A.K. Tyagi, who are stalwarts in their area, they have joined. There are so many others. If we start taking name of those, it will be again more time consuming. So thank you all participants. Dr. Vijay Yadav already has expressed his thanks. From my side, I express my thanks to the speaker, Dr. Mukesh Kumar Singh, and all the participants, and especially our past chairman, Dr. Kuldeep Kumar Sharma, who, of course, after the second wave of corona, he has some health problem, but he always makes it a point, though his energy gets dissipated in means attending some exhaustive things, but he has been throughout with us. And I thank him especially from my side. Thank you, Dr. Kuldeep Sharma, and thank you, everyone.
Thank you very much.
Thank you very much. Thank you, Professor Mukesh. Thank you.